So we talked before how to figure out the truth value of a formula of the form not A or B, A and B, and A implies B. But in general, we are going to see much, much longer formulas, which will have all sorts of mixtures of ands and nots and implications all over the place. So how do we go about evaluating a longer formula now that we know the rules how to evaluate every logic connective when we know both sides of it? In particular, in what order should we apply those connectives? If I put parentheses over everything possible, well, then you will know. But what if I don't put parentheses? What if I just write this formula as below? Should you do an and first? Should you do an or not, or the implication? What would be the order? So in arithmetic in school, you probably have seen those acronyms that they had, which I won't even try to pronounce. They were telling you that parentheses go first, then exponentiation, multiplication, division, addition, subtraction, and then you were using those rules in order to figure out in which order to add and multiply things. So here, when I'm writing things out, I'm throwing in another not very common thing, the unary minus, just because it will have an analog in logic. The negation will behave like unary minus. So one way of understanding how to evaluate long logic formulas and in which order those connectives go is to think of parentheses, just like in arithmetic, as taking the highest priority, the negation behaving like unary minus. So whenever you see negation, you kind of have to do it before everything else. After you've done negations, you do your ends. It behaves sort of like times. It actually behaves like times in many respects. The or behaves more like the plus. After you're done with that, you have if-then, which has even lower precedence than or. So just like you would do all your times before you do your pluses, you will do all your ors and ands and negations before you will do the implication. And when you have several of the same thing, you will go from left to right, again, just like in arithmetic. So for example, let me illustrate it here with just putting parentheses over everything in the way that you would if you do the right order. If you have this formula, you would do the negations first, and you see here there is a negation over a more complicated formula. So you will do this formula, and then you will put in, and then you would negate the result. Then you would do your and, or comes after the end, and finally your if-then, your implication goes last. Make sure you keep track of parentheses. By far the most common mistake, I think, both in logic and arithmetic, is forgetting to put the parentheses, especially when we start switching things in a couple of lectures, and then thinking that not belongs to just the very first letter and not the whole big formula after that. And you will get a different answer, just like 2 plus 3 times 4 is not the same as 2 plus 3 together times 4. A or B and C is not the same as A or B together in parentheses and C. You could check for yourself by plugging in A being true and both B and C being false. But let me show you something different. A way of writing down the formulas, or should I say, writing down the structure of the formula, which is a little bit more visual and shows you really how the formula is put together. Later on, when you're taking your algorithm and data structure course, you would use those things a lot in order to write programs to compute the value of arithmetic, logical expressions, and all sorts of other things. So let me introduce you to syntax trees. The way syntax trees work, they use the definition of what it means to be a formula or an arithmetic expression. And the definition said if you have two formulas and you take a plus between them, you got a formula. If you have two formulas and you multiply the first by the second, you got two formulas, right? So for example, when you're looking at 2 plus 3 times 4, it's a sum of two formulas. The first formula consists of just the number 2, and the second one consists of a product of 3 and 4. So let me show you what the tree will look like. So the very, very last thing we would do is a plus. And it will be plus of two things, one of which is a 2. And once we reach the 2, there is nowhere to go. We know that at this point, the value of what we have is a 2. But the other side is still a formula, which is a product of 3 and 4. So think about it this way. If you know the value of something, you cannot go lower than that. You cannot really break it into pieces. If you don't know the value of something, in order to calculate it, you just need to know the value of the thing at the bottom right and the thing at the bottom left, and you can get the answer. So let's do a few examples just so that you see how for different arithmetic formulas, which give you different answers, even the shape of those syntax trees is different. So we just did 2 plus 3 times 4. So what about 2 times 3 plus 4? So here you would do 2 times 3 first, and then a 4. So your formula is a sum of two things. The first one is a product of two things, 2 and 3, and the second one is a 4. Here is a tree. And notice how now we have more things hanging on the left of the plus than on the right of the plus. Let's try another one. 2 times 3 in parentheses, 2 plus 3 in parentheses times 4. So now we don't have a sum of two things, we have a product of two things. And the first thing is sum of 2 and 3, and the second thing is a 4. Here's how we write it. It looks very similar to the previous one, except at the very top you have multiplication. And the first thing you need to figure out when you're doing that multiplication is what is the value of the formula on the left side, which is the sum of 2 and 3. So I keep saying evaluate, evaluate, evaluate. How do we do evaluation once we got the tree? The way we do it is we go from the top, and we first look left, and if we know the value, that's great. If we don't know the value, we need to look inside of whatever tree is hanging off on the left and compute it. So for example, in the very first one, when we are computing plus, we first look at the left, and there is a 2 there. That's great. We know the value of the 2. That's 2. So now, in order to compute the plus, we just need to compute the value on the right. In the second example, we don't know the value of the thing on the left, so we need to go inside and compute it before we can do anything else. So for example, for 2 plus 3 times 4, in order to do the plus, you need to know both 2 and what 3 times 4 amounts to. Once you figured out that 3 times 4 is 12, you could get 2 plus 12, 14. In the second one, you first do your 2 times 3, you get a 6. And then there is nothing to calculate on the other side, 4 is a 4, and you just add them together. And similarly here, you first compute things on the bottom, and then you compute the thing on the top. You always do the thing on the top last, and you can never do something in a node of a tree, never can do an operator unless you've computed everything below that particular operator. So you may say, well, okay, we could use syntax trees to evaluate stuff, but how do we actually build them? In order to build a syntax tree, it's useful to look at a formula more or less globally. You look at the formula and say, what will be the thing that I will do last, the very, very last thing? Usually, if you say don't have parentheses for a moment, and you have pluses and times, your very last thing will be your very last plus. For example, in this case, the plus 8 will be the last thing you'll do. So you could look at your formula and say it's a sum of two things. The first one on the left of the plus and the second one on the right of the plus. So let me write a plus. And there are two things. So the second thing is easy, it's just a number 8, nothing to do there. The first thing, so now I'm kind of forgetting that there is a plus 8 somewhere, and I'm just saying I have 6 plus minus 5 times x. How can I build the tree just for this thing, forgetting about everything else? Well, this is a sum of two things. The first of which is a 6. And the second is a product of stuff. So what is it product of? Two things. Second one is x. And the first one is minus 5. So in arithmetic, you would probably just write minus 5 here. But let's think of minus as an operator. So the minus applied to 5. So now we got the syntax tree for this formula, and we could go and evaluate it. So notice that here, if I want to see what the value is for different x's, it really doesn't affect the parts of the formulas that are not involved in the way from x to the top. So for example, the 8 is still an 8. If I had big formula there that doesn't involve x and just involves number, I would calculate it once and just put the value, whatever, 8 in there, and I would never recalculate it. So let's try another example, this time with parentheses. When you look at this formula, what is the last thing you would do? Well, there are pluses that are outside of parentheses. There is only one plus, and this plus you will do last. So the whole formula looks like sum of two things. The first thing is a product of stuff, and the second one is actually also a product of stuff. So the first thing is a product of 4 and 6, so it's 4 times 6. And the second thing is a product of something in parentheses and 8. So what is the thing in parentheses? That's a sum. Notice that I don't really need to write parentheses here. I just need to know that the thing in parentheses is one thing that I'm multiplying by 8. And now I could just write the tree for minus 5 plus x. So minus 5 plus x, and I'm done. So the thing in parentheses, this one, becomes the separate little subtree of the big tree. This is what parentheses tell me. But really, once I figure that out, I don't need them anymore. And here is the final answer, and here is how you would write the formula if you were to show this to somebody who doesn't quite know which way the operations go, so you put parentheses everywhere. So far we just talked about arithmetic formulas, and you may be wondering why are we talking pluses and times and numbers 1, 2, 3, 4, 5 if this is a logic course. Well, this is because you're probably more familiar with arithmetic than with logic, and logic behaves very much the same way as arithmetic. So if you know how to draw syntax trees for arithmetic formulas, you would do it exactly the same way for logic formulas, just remembering the order. So, for example, let's look at a tree for A, or B, and C. So the very last thing we will do is a OR. It behaves like a plus. And it's an OR of two things, one of which is a A. And the second one is an AND of two things. The first one is a B, and the second one is a C. Let's do a tree for the formula A, or B and C. So now A or B is in parentheses. So the very last thing that you would do is a C. Your formula is something and something. So it's an AND of two things, the first of which is an OR of A and B, and the second one is a C. So now you see that those formulas really different because their trees look different. And actually the shape of those trees, if you look from afar and squint and then OR, should remind you of something. The first one is essentially the same shape as 2 plus 3 times 4, with a plus for the OR and a times for the AND. And the second one is the same shape as 2 plus 3 times 4. And you know that those will give you different answers. Okay, so let's try to work out a bigger and uglier example. So here is a long formula which doesn't have any parentheses at all except where they are absolutely necessary or the meaning would change. So outside of parentheses, it has a AND, it has a couple of NOT, it has a OR, and it has 3 NOT, it has a thing in parentheses, and it has the if-then, the implication connective. What is the very last thing we'll do? The very last thing out of those would be an implication. So we could look at this formula as something implies something else. So the implication will go on top. Now we could look at the two things under the implication separately. Let's look at the thing to the left. It has an AND and a couple of NOTs and an OR. So what is the lowest precedence operator here? The thing that you would do last? Well, I would say it would be an OR, because you would do ANDs before ORs, and you do negations even before ANDs. So it would be an OR of two things. Which things there are? The first thing would be an AND of things, and the second one will be a negation of something. So the first part would be an AND of things. Specifically, it would be an AND of A, AND of a NOT applied to B. And the second will be a NOT applied to C. So notice that in logic, we could put NOT not just on a variable, but on any kind of formula, which is kind of different from how unary minus works. Usually you don't really put unary minus on a formula, but you could sort of think about it when you're taking something minus something. It's almost like you're taking sum of two things, except the second one has a minus applied to it. So the second thing, it has a minus or negation applied to it. By the way, so at this point we are done with building a tree for the formula on the left of the arrow of the implication, and now we are building tree for the formula on the right. That formula is a negation of something, so let's put the negation on top. And what is that something that it negated? It's an OR of two things, A, C. So now we see the structure of this ugly big formula, and it tells us that in order to figure out whether this formula is true or false, first we need to figure out whether this formula on the left, the one with the or on top, is true or false, and then the formula on the right, the one with the negation. And then you keep going. Okay, so let's try to evaluate stuff. So first, if A and C are both, so first we put in the values of the variable. And you could see the green for the A and the red for B and C. That's because we started with A being true and B and C being false. When we evaluate something, we give it a value. Like in arithmetic formula, I could say that my x is equal to 1. So let's see what the value of the whole thing is when my x is equal to 1. So here, in order to evaluate the or of things, we need to evaluate what's on the left and what's on the right. What's on the left, we know. It's just an A, and the A is true. So what's on the right, it's the end of two things, which are both false. So the first thing we would do is we say false and false is false, and make this end red for being false. The next step is to evaluate the or. So we have true or false. Or is happy if at least something is true, therefore the whole thing is true. One thing that people do a lot in programming is if they see something like this, they say A is true, I don't need to worry about what the end of stuff or the right subtree of the thing is. I know if A is true, then the or is going to be true. I don't really need to bother evaluating it, but let's do it just for practice. Okay, let's try another example, the second one. So now we have, again, A true and B and C false. This time, the first thing we need to evaluate is A or B. A is true, B is false, true or false is true, so A or B is true. And now we go to the end of two things. The first of it is true, and the second one is false. So true and false is false, so the whole thing is false. So you see that the whole formula becomes false. This is yet another proof that those two formulas are not the same, because you plug in the same values for A, B, and C, and in one case you end up with a true, in the other case you end up with a false. Okay, let's do that big formula just for the fun of it. So it was a something implies something. Let's look at the thing on the left of the implication. Okay, it's still big. It's an or of two things. Okay, let's see what the first part of the or. It's an and of two things. And now we could actually start calculating. The left part of the and we know. It's A, and A is true. The second part, the right part of the and, we don't know, because it's some operation applied to B. So let's apply it. It's not of B, not of false is true. So now we know that it's an and of two things, both of which are true. So and is true. Okay, now we are trying to do the or. We have the left side, but not the right. We go in and figure out the right side. It's not of C, not of false. That's true. Now we can do the or. Okay, we are done with the left side. Let's do the right one. True or false will be true. Negation of true will be false. So now we know that the right side is false. Finally, we say we have true implies false. Now that's the only situation when the arrow if then will be false. So the whole formula is false when A is true, B is false, C is false.